where theta is the angle between R and F. So let's look at that in action and see it in a simpler fashion. So going back to this, if I have this force here, we'll call that force 1, and this force here, that's called R1. Then if I wanted to know the torque, what I would be doing is doing that vector cross that vector. Now, if you'll remember something about when we did cross product, if I want to know what that angle is, I have to draw the vectors in a specific way. Yep, if you remember, that way is concurrently. So F1 and R1, and there's that angle. Theta would be 90 in this case. And so that would yield a maximum result because sine of 90 is 1. Now, if I had force 2, and that would be R2. Looking at that, once again, if I draw those two vectors concurrently, F2 and R2, my angle between those is 180 degrees. Sine of 180 is equal to 0. Here, right, sine of 90 is equal to 1. Now, if I had this vector here, and that would be my R3, and let's say that this is a 37-degree vector. Looking at that when drawn concurrently, there's my force 3, I'll call that F3, and here is my R3. We know that that's a 37-degree angle. Technically, what's that? That's going to be 143 degrees. We put that in. Now that geometry gets awkward real quickly, so I'm going to show you a much simpler way of doing all of these. And that is going to be using something that we're going to call the lever arm distance. So the lever arm distance, we'll call it L perpendicular. I'm going to define it first, is going to be the shortest distance between the axis of rotation and the line of action of the force. So, what does that mean? Well, here, let's go back to it. Same examples. Well, that's a little off, but F1 is here, and if I draw the line of action, and this is the axis of rotation, the shortest distance between that is always going to be a perpendicular distance, because the shortest distance between two lines, or the shortest distance between a line and a point, is a line perpendicular between those, right? So that's going to be L perpendicular 1. If I have this here, F2, notice its line of action goes through the pivot. So its perpendicular distance is going to be, L perpendicular for 2 is going to be 0, because its line of action goes through the pivot, and therefore it is not at all off of there, right? And then our third one here was something like this, F3. Now technically, there's the line of action, and there is L perpendicular. And that could be a really annoying geometry problem, but we're going to make our lives simpler, because I can split up F3 into its components. And so here's F3y, F3x. You'll notice L perpendicular for F3x is going to be 0, and L perpendicular for F3y is just going to be this distance here, right? So hopefully what you're seeing is the following. For horizontal forces, L perpendicular has got to be vertical. And for vertical forces, L perpendicular has to be horizontal. And so we then can end this by saying the magnitude of the torque is equal to the magnitude of the force times the magnitude of the L perpendicular. And so that is nice and simple there. A lot simpler than dealing with the geometry with the cross product. And so this is going to be the way that we're going to solve problems, as we will see.